This chart shows Indonesia's blueprint to achieve net zero by 2060, requiring a massive scale-up of renewable energy to 587 gigawatts. Look closely at that final year. The volume is dominated by intermittent sources, specifically 361 gigawatts of solar and 140 gigawatts of battery storage. Integrating hundreds of gigawatts of intermittent solar power into a rigid legacy grid virtually guarantees catastrophic systemic failure. Traditional power architectures rely on coal or gas plants running continuously to maintain a steady baseload. When heavy cloud cover drops thousands of megawatts of solar supply offline in seconds, those heavy turbines cannot spin up fast enough, causing cascading voltage drops and blackouts. Avoiding that collapse means PLN, the state utility, cannot simply plug green energy into old infrastructure. They must completely disassemble and rebuild the physics of their grid from the ground up. This structural overhaul is codified in their Accelerated Renewable Energy Development, or ARED strategy. The success of the 2060 target hinges entirely on what happens right now. The immediate, aggressive retirement of coal and deployment of green infrastructure is actively mapped out in the new Green RUPTL for 2025 to 2034. This graphic from the Green RUPTL details the exact capacity additions planned over the coming decade. The utility is preparing to build and connect a total capacity of 69.5 gigawatts of new generation. The pivot is visible right here in the allocation. 76% of that total, representing 52.9 gigawatts, is exclusively dedicated to renewable generation and storage. Because the network still requires continuous power to replace retiring coal plants, a massive portion of this allocation relies on dispatchable green sources, specifically 11.7 gigawatts of hydro and 5.2 gigawatts of geothermal energy. Building that physical capacity over a single decade requires an unprecedented volume of capital. This chart outlines the financial reality of the transition. The total estimated investment sits at 2,699 trillion rupiah, structurally divided into commercially viable generation and non-commercially viable support infrastructure. While power plants generate direct revenue, the underlying transmission lines, substations, and rural electrification efforts, costing 434 trillion rupiah, are non-commercial necessities that the state must absorb to make the grid function. This specific capital requirement forces PLN to simultaneously re-engineer the physics of how it moves electricity and the financial mechanics of its balance sheet. The physical engineering challenge starts with strict geography. Indonesia's densest populations and highest industrial energy demands are located on Java and Sumatra, but the largest untapped hydro and geothermal resources sit deep within Kalimantan, Sulawesi, and Papua. This schematic maps PLN's current operational flow, moving sequentially from primary energy extraction through generation, transmission, and final retail distribution. To bridge the geographical divide, the state is designing a national supergrid. This inter-regional transmission network utilizes high-voltage undersea cables to export surplus green power from remote islands directly into major industrial hubs. Moving unpredictable solar and wind power across vast distances requires real-time digital balancing. The network must constantly calculate exactly how much power is being generated and consumed down to the millisecond. This diagram outlines the digital architecture required for that balancing. Integrating advanced metering infrastructure and automated smart transmission creates a neural network capable of predicting demand spikes and rerouting supply instantly. Even with perfect digital transmission, a sudden drop in wind speed or a heavy storm will instantly erase gigawatts of active supply, threatening immediate grid failure. This operational gap is why battery energy storage systems and pumped hydro are critical components. They act as massive shock absorbers, storing excess power during peak production and releasing it instantly when supply dips. Massive utility-scale storage systems instantly discharge gigawatt-hours of power to correct rapid frequency drops and maintain baseload stability. The supergrid transitions the country from a static one-way power delivery pipe into a highly responsive, multi-directional energy routing ecosystem. Yet all of this physical engineering hits a hard mathematical constraint. A single state-owned enterprise cannot absorb 2,699 trillion rupiah in capital expenditures without collapsing its balance sheet. To survive the scale of the RUPTL, PLN is shifting from operating as a pure monopoly builder into an ecosystem orchestrator designed to absorb global green financing. This flowchart breaks down the shift in financing structures. Historically, the utility used an EPC model, engineering, procurement, and construction, where the state owned the asset entirely and held 100% of the financial risk. They are replacing that with a strategic partner framework. Here, capital risk is shared with external investors, while a PLN subsidiary maintains a minimum 51% controlling stake in the generation asset. For maximum capital injection, they utilize the Independent Power Producer Scheme. This creates a special purpose company to house the project, capping the state's mandatory ownership at just 30%. Diluting state ownership creates the legal vehicle required to attract massive institutional green bonds and specialized international funding mechanisms, like the Just Energy Transition Partnership. Massive injections of foreign capital instantly accelerate physical infrastructure development, transferring operational risk away from the sovereign balance sheet. Reaching that 52.9 gigawatt renewable target means PLN must now operate less like a traditional power plant manager and more like an investment bank, meticulously structuring isolated asset vehicles. Scaling this massive green supply creates a fatal economic imbalance if consumer demand remains permanently tied to subsidized fossil fuels. To ensure there is a paying market for all this new clean electricity, the state is actively forcing a demand-side pivot, driven primarily through the mass incentivization and rollout of the electric vehicle ecosystem. This data outlines the specific government projections for that shift. The roadmap mandates the mass adoption of millions of electric vehicles, alongside the nationwide deployment of induction stoves and electrified agricultural equipment. Simultaneously, multinational industrial consumers operating in Indonesia face strict internal ESG mandates. They are actively demanding renewable energy certificates, which guarantees offtake revenue and drives even more private IPP investment into the grid. Electrifying mass transit and large commercial fleets directly cannibalizes fossil fuel demand, permanently altering the national carbon footprint. This is the actual mechanics of the ARED strategy. It is a self-reinforcing loop combining supergrid engineering, IPP project financing, and aggressive demand-side electrification. Indonesia's 2060 net zero target operates beyond political rhetoric. It is a rigid, mathematical necessity, and the physical engineering required to achieve it is already breaking ground under the Green RUTL today.